Here we are at, I think this is the 4th session of our water treatment tutorials being supported by the Operators Without Borders of British Columbia, and our tutor is Mike Firlotte. Good morning, Mike, and welcome again.
Good morning, Ignatius. Thank you. It's nice to be here again this morning. It's 4 in the morning for me. It's a lot warmer than it was last week. Only -4 today with lots of snow. It's probably a lot more cold than where you guys are. So I am kind of jealous that it sounds like it's in the 20s where you are. So I'll try to stay warm over here. It wasn't as bad as last week. We had -27 midweek after our session last week. And that's very cold for water treatment and all the reservoirs and creeks and everything we'll learn about today. They're quite frozen, and that causes some issues here in Canada when things start to freeze. It's hard to move water around when it does, and even in the pipes, it does freeze a fair bit. I'll just set up my presentation, so just bear with me here as I share my screen. Pretty small group this morning, but it's good to see everybody. All right, make sure I have the chat up here. Can everybody see the presentation okay? Could you give me a thumbs up if you can, just to make sure I have it right? Thank you. Perfect, awesome. Okay, so this is week 4, and I know we kind of went out of order with the last week, and that's what we'll kind of touch base with that. So the plan going forward is we're going to kind of go through right from the water sources, which will be today, and we're going to talk all about different types of water, getting it to your treatment. As we get it to the next sessions we'll be dealing with is how do we get all the things out of the water that the environment introduces. And so that's going to be quite important. So that'll be the next few lectures. And then we'll deal with some specialized treatments, some filters. Usually we put in disinfection at this point, but we covered that last week. And then we'll talk a little bit about once it leaves the treatment facility and goes to your customer, and it's done all different ways. Again, for those of you who are new to me, I've been doing this water treatment for close to 23 years. I've been an instructor since 2005, and I do that on my own time. I take vacation time to take that time to teach. I have experience as a director, a manager, and of course an operator, and I've been an operator since almost 1997. I became a water treatment plant operator. Also a former director of EOCP. 2 pictures here are quite interesting, and it's quite fitting for my discussions today. People think, you treat water, you put it into some pipes, and off it goes. In the picture here on the lower right, this is a plant I go to in northern Canada, and where they treat the water. This is from a well. So the well is actually underneath this blue building that you see here. They treat the water inside that building, and it's so cold there. We're talking -52 Celsius. So you can imagine how cold that is. And the water cannot go into the pipes. There is no pipes. It's so cold. So they go into these trucks, and the trucks take the water and they deliver it into tanks inside people's houses. Another truck comes around later to take the wastewater away in another truck. But because it's so cold in some places in Canada, you can't even bury the pipes in the ground because the ground is too frozen. So we do have our own unique challenge to getting water. There's lots of surface water at a place like that, but the problem is everything is frozen. So you have to get water from somewhere. In this case, they have to drill very deep into the earth to bring water to the surface. So that brings us to our lecture today. We're going to talk a little bit about water itself and the environment. We'll talk a little bit about the environment itself and some of the things that happens in that environment that could potentially contaminate your water. What happens out there in the contamination will dictate what kind of treatment you're going to need. Surface water and groundwater, which we'll talk about in a few minutes, have to be treated. So something with lots of minerals will be treated differently to water that, say, has some color in it. So this chapter here, we're going to talk about basic water quality, the contaminants, those contaminants gets into your water, and how do we get this stuff out of here? We should look at different types of water, and I'm interested too if you guys can put into the chat portion, where does your water come from, right? Does it come from a well, or does it come from a surface water, like whether that's a creek or a river or a lake or anything like that? I'd be curious to know if you want to put it in the chat function. We're going to talk about some of the different, like major challenges, especially with groundwater, and that's going to be, again, hardness, and it might be different type of minerals. And we'll learn about what a watershed is and what's important about learning about a watershed. A complete assessment when you're going to design a new plant is really important, because you want to make sure that the desired treatment is the correct treatment for the water you're dealing with. You should underline these two things here because it's quite important. You have, let me just get my, my little drawer. Surface water here, underlining, circling, and groundwater. Those are the two most important things. So when you deal with testing purposes, especially when you write the test, they're going to look at those two things. Surface water really is anything that you can see, if you can think about it. And that's going to be all lakes, rivers, streams. If you can see that water, it's going to be termed surface water. And it has to be treated much differently than what we're talking about groundwater. The groundwater basically is stuff underground. So that's when they actually drilled a well and water comes from the ground. You don't know the water, you don't know where it comes from. And that can be a problem sometimes. If I can remind you guys to please mute your microphones, please. It makes it a lot easier to hear everything. Thank you. Okay, let's talk about the difference. Now, in a testing situation, this is going to be really important, okay? These are pretty typical, but I've seen it sometimes that it's not. Surface water is soft, which if you want to put beside soft, make a little note to yourself. Soft water means it doesn't have minerals in it. And if it has too much minerals in it, it gets too hard. So basically soft water is how many minerals are in that water. Turbidity is really important too, but think about turbidity doesn't mean dirt. It doesn't at all. And we're going to learn a little bit about that in next week's chapter. But turbidity means cloudiness of the water. It has a milky appearance, or a yellowy, milky appearance, not dirt. The next one here, suspended solids, that is the dirt content in the water. Color, of course, is a big one, and microbiological. Because surface water is open to the atmosphere, it's also open to human contamination. So, animals or people will, you can boat in it, you can walk through it, things happen. And that's, creates a lot of contamination. We're going to talk a great deal next week about color, because color is one of the hardest things to remove from water, right? So when you go home, you should try this little experiment and let me know how that works. Take almost, if you have a clear container and you're going to make some tea. And tea is leaves, right? Basically in a tea bag. It's tea leaves. You put that tea leaves in a clear cup and you pour hot water over the leaves. What happens? Colors, right? Colors go into the water. It's that tea color. It's exactly what happens out there in nature, right? Those acids and those tannins, the water, and they stay there. Now think about this. If you leave this container of tea on your counter for the whole week, will it separate? Or will it stay looking like tea? And the answer is it will stay looking like tea. If you put that through a filter, would it still be tea? It will. It doesn't separate. It becomes one liquid. It's a colored liquid. So what we need to do is figure out why that is, and we need to figure out how do we get the color out of that water. And that's the stuff we'll be learning next week. Let's switch over to groundwater here. The thing with groundwater is that, it was surface water at some point. It made its way into the ground and it's been traveling. It could travel through the ground for hundreds of years. Because of that, though, it's in contact with minerals in the water. So instead of being soft, it's now harder, which means it has a lot of minerals in it. But also underground, it can also absorb some gases and sometimes H2S gas. And that's that sewer smell that we smell sometimes. Because there's not a lot of leaves or organics that mix with the water, it doesn't have a lot of color. High hardness, like we talked about, because it's got lots of minerals. And because it's underground, and bacteria, not a big fan of being underground and having no oxygen. There's not usually a lot of microbiological problems. You can see here between the two waters, we would have to treat this differently. We're not going to put something that removes hardness in surface water because it doesn't need it. So it's important to figure out how our water is treated and what our water source is, so we're taking out what's in that water. We'll talk a little bit about the hydrologic cycle. And that always shows up on some tests, right? Always. So pay attention to this part here. This is the relationship between surface and groundwater and the water moving through the atmosphere, right? So water is a big cycle, and we'll look at that in a few minutes here. What's important to note here, let me just get my little pen here. Oh, there we go. You can see how this is going to work. You see, let's start with the cloud in the sky here. So we got this cloud, right? And how clouds are formed is that evaporation. And that's basically water, whether it's from all the water sources that we can, it evaporates, right? It's like boiling a kettle, it turns into a steam, right? That moisture goes up and forms clouds. When those clouds get heavy or they get colder, they're going to condense and they're going to rain. Now, precipitation is what they call that. So for you guys, it would be rain. Today, for me out here, it's going to be snow. I'd much rather have rain. When it hits the ground, and we'll talk about this a little bit more, when it hits the ground, it does a couple of things. It can actually soak into the ground. And when it soaks into the ground right here, you can see it. This is called infiltration or percolation. Think about the coffee, right? When you pour sometimes water through a coffee filter, it percolates down through the coffee. Same idea. This is going to infiltrate the ground, percolate down through, and it will join the underground lake network, or what they will call an aquifer. We're going to see that in a few minutes. Sometimes, though, it doesn't do that. It will flow across the land as runoff. And that's where it really picks up a lot of contamination. So think about a street, right, that has cars and pollution. And as that water runs across that street, you're going to see that it's going to pick up the oils and the dirts and all the stuff that's been on the ground and on the street sidewalks, and wash it into the nearest water source. And that could be a small river, a creek, or into a lake. So we're going to take a look at that. One big thing it's affected by is the land features, right? And places like, say, in Western Canada, here, there's a lot of mountains. And definitely in a place where there's lots of mountains, it changes the currents. Where you guys are, you will be affected more with the ocean currents. And that changes the water patterns or the weather patterns. And for you guys down there, I would imagine you get much crazy weather when in regards to wind and rain events than we will here. We would get more snow events. We see a lot of our snow land in the mountains, so we get the currents associated with that. It'll be different than places that are in midland, so they do not have access or anywhere nearby that are ocean and or mountains, and they're going to have a completely different weather, different rain pattern. Where I am here in the west coast of Canada, we get a lot of rain just because of the mountains, and we're fairly close. I'm only 3 hours away from the ocean. Unfortunately, like all things, there is contamination. So contamination can occur throughout this entire hydrologic cycle. And that's a problem. And that's something to be aware about. Where are potential points of contamination? It can be diluted, concentrated, or transported through the cycle. And again, it will at some point affect your water quality and also affect the type of treatment that you will have to have. It sounds like in the chat function here, most of you are on surface water, so that's interesting. So lots of chances of contamination. So we'll definitely, when we talk about how we treat water, especially next week, it'll be very important to tune in for that one, because we'll talk a lot about how we get rid of that contamination. If I can get you guys to mute, please. Thank you. Okay, so what we can do here, in this particular picture, what we see is some potential points of contamination. I will, well, hang on.
Taniqua, could you please mute your mic? It's disturbing the meeting. Thank you.
I got competition in teaching. All right, so this picture here that you see, you have contamination. And you can see here, there's a whole bunch of things that can contaminate this water cycle, right? And we'll just look at a couple. One big one is mining over here. Wastewater, right? And the thing about wastewater, any sort of wastewater, that it could go into the ground. You can see how this particular one went into the ground. Also buried garbage or landfill in the ground. One is fuel, right? Like fuels also, gasoline station, petrol, all that kind of stuff. Farm here, pesticides and fertilizers, all that stuff, even sewers, anything like that. Anything that's buried. You can see this layer here, this right in here. This is an unconfined freshwater aquifer, and this is where people's drinking water comes from. You can see here he has a well right here. Water's going to travel through here and up it goes and service all your community. You have all this pollution that could happen. And it's always really important to understand, because people go, well, I don't get my water from a well, so it doesn't matter. But it does, because this water here, even though it's groundwater, will supplement surface water. It has to, at some point, flow into the surface water. So surface water and groundwater are very connected. So if there's a landfill or waste lagoon or something that's going to have contamination, it eventually will enter your surface water source, and vice versa. If you have contamination in your surface water, sometimes it could come into your groundwater source. So they're always connected, and it's always really, you should take good interest in just, the history of where your water comes from. That's surface water or groundwater. Understand where there was landfills or wastewater or any sort of industry that can cause issues in your whole system. Very, very important, because it's all connected at the same time, even though it might not seem so. Let's talk about the components of the hydrological cycle. And the two big ones are evaporation and transpiration. Now, we know what evaporation is. We talked a little bit about that. The transpiration, though, is an interesting one. And I'll draw you a little picture, and I'll try to make it the green. I'm not a very good drawer, but bear with me. So this is a tree. It's a really bad looking tree, so I apologize. And I'll make my blue water here. Okay, so we got some water. Normally, evaporation, water turns from the liquid form to the vapor form, and up it goes and evaporates. In transpiration, what happens is it gets sucked up through the roots of the plant. It goes through the plant, and the leaves of the plant, it evaporates off the leaves. So it comes up out from the roots through the plant, and that is transpiration from the roots of the plant. That's a tricky question. I see that on the test sometimes. So always be aware of that. It's just like evaporation, only it goes through plants. When it gets into the sky, right, and it starts cooling off, it comes as condensation. And condensation, where it's turning from the water vapor back into a liquid, okay? That's basically what it's doing. When it does turn back in that liquid, it gets really heavy, and it's got to drop back to the earth. It drops back as precipitation. And again, precipitation can come at many forms. Water for you guys in the form of rain. And for me, I see it as rain. Sometimes right now, no. but there's also, you can come as hail or sleet or any sort of in between. But basically, it's water falling from the sky. We do know that it's going to infiltrate into the ground. That's the first thing it's going to do. It's going to go down and it's going to, what they do, recharge your groundwater. That's what feeds that groundwater. So it infiltrates the ground and it percolates through the ground and meets up with the aquifer. Sometimes it rains so hard that it can't all infiltrate through, so it moves across the land as surface runoff. And that's probably the worst because it picks up a lot of really nasty things as it does that. Let's talk about these a little bit more. Again, pretty easy. All Earth's surface evaporates to form clouds. That's part of the cycle. And it comes back as precipitation. That moisture is absorbed by the soil and percolates into the ground. Eventually, it could also go runoff and it joins up into your surface water. It's funny to note though, a lot of the water that falls as precipitation gets re-evaporated back up long before it ever hits the ground, especially in a warmer climate. And that gives that humid, you know, especially I'm sure where you guys are, it's quite humid. So here in Canada and where I am, it's very dry and there's not a lot of evaporation or moisture in the air. We'll keep going on precipitation. So the water vapor forms the clouds in the sky then. Under the right conditions, right, it condensates and deposits water back to Earth. And this is our precipitation. It occurs when all these water droplets or ice crystals, because if you think about it, in the high atmosphere where the clouds are, it's quite cold and it could be ice crystally. They're gonna fall again as rain, hail, sleet, snow, mostly rain though. And we talked about what it can do. We know it can join a water body, and that's going to be your surface water sources. It can migrate as runoff, infiltrate into the ground to become part of groundwater. We talked also about that it will evaporate again. Used up by the vegetation. So if you have a lot of vegetation in your area, it uses that up. And again, we'll see that potentially get reintroduced as transpiration, and again forming the cycle again. Okay. We talked about the runoff, and when you can't infiltrate any more water, it gets saturated, right? That water will flow over the land or over the streets, and this is that runoff, and runoff is pretty nasty. Unfortunately, when it does reach its final destination, and that could be your surface water, drinking water source, or the river, or the water source that you're taking your drinking water from. And it gets really nasty. In this example here, you can see in a really heavy rainstorm, look at that, right? It might flow across the land here and take a lot of the dirt with it. So this water has wrong with it. It has color, it has suspended solids, and it has turbidity. And now we got to treat this water, which is our drinking water source. So that's always a problem. So always think about that, because it can cause a lot of problems. Let's talk a little bit about the infiltration. Infiltration takes place when water penetrates through the Earth's surface. Percolation takes place again when the residual water left after the soil has been infiltrated. It kind of keeps going down in to the groundwater. So here's the big difference here. Let me get my pen. There we go. So precipitation comes down. You can see that if it's really shallow, it infiltrates. It infiltrates the ground or its surface runoff. So you can see that it's headed for this river. And that surface water is going to be pretty brown, and it's going to have some contamination into that river. The infiltration will follow this layer, a saturation layer, and basically it's going to move fairly quickly through and come out into the river, and that's infiltration. If it keeps going, it's going to percolate over time into the groundwater flow. And you can think about the groundwater flow as an underground river. It moves really, really, really slow. And it always moves towards a body of water. So in this case here, that groundwater is moving towards this river. And it actually becomes part of that river. And that's why I keep saying that surface water and groundwater are very closely related, because a river typically is a mix of groundwater and surface water together. And it will change throughout the year. Most of our water here in Canada, for example, comes from snow melt. So snow melts on a mountain or a hill, and over time it will melt and make its way to through a river to a lake, say for an example. In the wintertime though, everything's frozen. So a majority of that same river is going to be fed from underground groundwater. So definitely if people who are taking water from both that river during the winter and the summer will have completely different water quality and have to treat it differently. So always good to understand that. Again, here's another good example with the picture. Here you can see the runoff into infiltration and the percolation. And that's your evaporation. This body of water we see right here, you know, the sun shines on it, the molecules are heated by the sun, they turn into a vapor, up they go, right? They go into the atmosphere and form those clouds. Again, always to remember that it can come as transpiration through those trees there, or evaporation from the surface water right here. Again, transpiration, capillary action draws that water from the soil and through the plants, and water's passed to the leaves where it's off the leaves into the air. So that's really important. Condensation, again, it's another state change, right? We had evaporation, that's that liquid to vapor, up it goes. When it's up in the clouds, now this water vapor is going to go from a liquid or a vapor to more of a solid or a liquid. Water vapor meets the cooler air and forms tiny droplets of water or moisture. As these water droplets collect, clouds are formed, and when it gets really heavy, it falls out of suspension and falls to the earth as precipitation. This is a super important term to learn now, aquifer. An aquifer is what groundwater is. It's an underground reservoir. The actual term and term that you might see in a test is any water-bearing geological formation. It's an underground reservoir, right? That reservoir is moving. So it gets recharged by the rain that's percolating through, but that water's always moving, and it's moving more and more. It's moving towards some sort of discharge, whether you put a pump there or it's discharging into a stream. And we'll see a picture in a second on that. You can talk about a little bit of a spring. A spring are generally formed when a flowing body of water, groundwater intersects a hill. Sometimes you'll see a hill and there's water pouring out of the side of the hill, and that's groundwater discharge. That's groundwater coming out of the ground. Sometimes too, if you're digging a hole and seeing water, that's the indication that's groundwater. So let's take a look at this picture here. Okay, this is always a good. Okay, so basically here's what you have. And when people say that groundwater and surface water aren't, you can see how it very much is. We'll take this stream, for example. You can see how if it would rain, and I'll use blue. So if it's raining here, it will percolate into the ground, but it could also run off into what we see, the surface water. In this stream here, you can see that it has surface water and groundwater from underneath. That's always typical, whether it's a stream or a river, always two sources of water going into there. So always remember that. Another thing to think about here is that the water in this first layer is called unconfined. And we'll talk a little about that in a few minutes. It's not confined, which means it can move. It's free to move towards discharge. In this case here, somebody put a well right here. And because somebody put a well there, it's just like, say, if a bathtub, right? And if you take the plug out of the bathtub, what happens? The water's going to move towards the drain. This is the exact same thing. When I take that plug out or have a point of discharge, this well, for example, water in this confined aquifer is going to move to. It is also going to move towards the stream. So that's going to be two flows of water. We got to be really careful though. One thing that happens and people don't necessarily realize it is that, and I'm going to use brown. Say I had some contamination right here. And this could be maybe some wastewater or garbage dump or something there. Now, all of a sudden my water is moving towards this way. And it's basically going through this wastewater or contamination's moving towards my pumped well right here. So always understand what is in your area or in your aquifer, because it could get drawn into that well. This water up here in this unconfined aquifer, because it moves, it might not be in there for very long. It might be months, weeks, you know, but definitely not a long time because it's very fluid, it moves around. These brown layers here in this picture, right here, is bedrock or some sort of clay, and seal it up so it doesn't, water can't move around. If we're in something called the confined aquifer, and this confined aquifer means that it's got, it's like a vessel. It's sealed up pretty good. It's hard for water to get in and it's hard for water to leave. And so it doesn't really move a whole lot. It doesn't necessarily contribute to any surface water, or not a lot of pumped wells use it. It's a little bit deeper. it could stay in there for years, years. Or even a deep, deep, deep water could be in there for centuries. And I've seen some groundwater that people use that's in the ground for hundreds of years. And they do tests on these waters to see how old that water is. Imagine, it took 100 years from the time it entered that aquifer to the time it came up your well or discharged into surface water. So that's a long time. And during that time, it could touch a lot of minerals and could be really, really hard and have a lot of minerals in it. All right. So when excess water infiltrates into the ground, it percolates towards this aquifer, right? Or groundwater. That's what it is. Aquifers always flow towards the site of groundwater discharge. And we saw in that example in that picture, right? That there was two here that pumped well, and in this case. It can supplement surface water, and it usually does. So really important to understand that surface water and groundwater are connected. They can directly discharge to the surface again, and at springs or some sort of land mass or a pool. You'll see all of a sudden there's a lake in the middle of nowhere. Sometimes that's what feeds those lakes. We saw the saturation in the unsaturated zones. And so there's some important words here that we should talk about. Water table's a big one, right? Water table is considered the top of the groundwater. That's when groundwater starts. So if you're digging a hole and it's nice and dry, and all of a sudden water starts coming into your hole that you just dug, you've hit the top of the water table, the top of the groundwater flow. It's also called zone of saturation. So in this picture here, this unsaturated zone is basically the zone that the water percolates through to meet to the water table, or what we're going to call the saturated zone. The saturated zone is a fancy way, that's your aquifer. That's where the water is. So if I'm putting a well in here, I better make sure I'm in the saturated zone, because that is the aquifer itself. The unsaturated zone is the length it has to travel, the water, to get into the saturated zone. So again, here, unconfined aquifer, the upper boundary or the top of the water table. Again, it could rise. If there's more water in your aquifer, it will rise up, or in times of drought, this will lower right down. It's also called water table well or shallow well. When we talk confined aquifer, it could be known as artesian or pressure. Because it has confining layer, there's bedrock or something, it can't move around. So if more water enters it, it pressurizes up. It's like a soda can, right? You can only get so much, and if you shake that up a little bit, the pressure rises up and the water will travel by itself. You almost don't need a pump to actually do that. When we go back to our other photo here, if this particular pumped well was down here into the confined aquifer, this is under pressure. So every time water enters, water's got to move somewhere. Sometimes it will move up here all by itself because there's so much pressure in this layer. And that's what it's called, adhesion. And that's great because you don't need a pump. Some places have a pump here, but this definitely helps. But in times of drought, if this is all the groundwater is depleted or starting to get low because of drought conditions, then you won't have as much pressure. And sometimes you need a lot of pressure to get that water up to the surface. So always be careful with artesian. Sometimes it will flow and sometimes it won't. Let's talk a little bit about some groundwater terms. And these show up on the tests quite regularly. So you pay attention to these ones. When I put a well in there, and I'm gonna make sure my well is sitting in the unconfined zone, just like this. If I punch that well in, it's gonna have, a static water level. The pump is off right now, and it will have a static water level. And you'll measure that level. When you turn the pump on, it will do something called a drawdown. The water level will lower to a pumping level here. The difference is the drawdown. So it's this many meters, you turn the pump on, it's gonna be a lower. And that's the drawdown. Think about when you turn your, again, back to your bathtub, right? If you let that plug go, remember it makes that kind of that funnel, looks like a whirlpool or a tornado looking, right? And if you're looking down, that's what it is. It's the drawdown. It's creating a vacuum, and it's creating that same thing with here. You're gonna create that same thing. That's that drawdown. And if this changes, your static water level changes, or the water level that it goes to when it's pumping, if those things start to change, you should take a look at what's going on. And there's a number of things that it could be. It could be some issues with your well. It could be because there's drought, or on the opposite, there's almost too much water, and those will change static water level and your drawdown or your pumping water level. Also the cone of depression. And if I looked at it, you know, and again, I go back to the tub, right? When you put that, take that plug out, it makes that little whirlpool. And if you look over it, right, it has, clear that. If you look below, it will have that circle, right? And the width of that circle is the radius of influence. It's how much does that influence bringing that water to it. The bigger the circle, right, the bigger the influence in the area that you have. And that makes this cone of depression. And you can see it looks like a cone, right? There's the top, and there's my drawing. There we go. It looks like a cone right here. That's the radius of influence down. So it makes kind of a triangle shape. And the width of the triangle is your zone of influence. And there's your drawdown, or your cone of depression. And that, you know, that funnel shape that dictates the influence on the water around it. The bigger that is, the more powerful it is, the more it's going to create vacuum and to suck the water towards that well. And hopefully there's water coming. You know, the biggest problem is if there's contamination, it's going to get sucked in. So you got to be careful, and you don't want to do too much. For those of you who had a milkshake or some liquid that has, it's very thick, and you take a straw and you're trying really, really hard to suck that drink up, and all of a sudden it doesn't work. What happens to the straw? It gets, collapses. And the same thing will happen here if it tries too hard. The ground will actually start to collapse, and you don't want that. Some other things that are really important are the residuals drawdown. And that is the distance between the original static water level. Oh, what happened here? Let's try that again. Sorry about that. All right, here. So residuals drawdown and well yield. So the yield of a well on this particular one is a measure of the volume. And that's how much water. And you guys will see it as liters per minute or liters per second or cubic meters per hour. And it's measured. How much does that well produce? Recharge rate too is really important because what happens is that you saw that the first water level back here was the static. And when I turned it on, it was the pumping. But when I turn it back off again, it has turned to the static water level. And whenever it turns, that is the recharge rate. How long does it take for that water level to come back to normal again? And sometimes if it doesn't return right away or doesn't return fast enough, that could mean that there's some problem in the supply or getting water back to that well. So always really important. The biggest one though is this one, specific capacity. And this is a measure of the well yield per unit of drawdown. So that's how much water can this produce for every meter below the surface this well goes. And that's a really important one. Now, we'll take a quick break in a second here, but I'm going to leave you with this one question during the final, and then we'll go over it. So just hang tight. I'll get you that question. I will just... It'll be the hardest question you'll get all day, but it'll be interesting to see how you do. Now, this particular question I always give to some of my new students, and it's very typical what you're going to see on the test. Since we just talked about specific capacity, I thought I'd give you this question. It's designed to make you think, and I'm not expecting you guys to solve it right away. But take a look at it. I'm going to give it to you, and we'll give you a few minutes, and then we'll take a break. So let's take a look at that. I'm going to give you this question right now. There we go. Let me know if you can see that. It should say well number 7. Give me a thumbs up if you can see it. Awesome. Learn all day. So take a look at that question, and I want you to kind of play with it. So I'm going to give you a few minutes to work through this question. We'll solve it together here. I'm going to give you 3 minutes to do this question. It shouldn't take you any longer than 3 minutes, and then we'll solve it together and take a quick break. But I'll give you a couple of minutes to solve this question. Okay, with a show of thumbs up, how many people thought that this was really hard? And that's okay if you did. Give me a thumbs up if you thought this was really a difficult question. Yeah, perfect. How many people thought this was really easy? So I'll teach you a little bit about these questions. Here's the thing. So this is a typical question you're going to see on the exam. And I threw this in here just because I thought it'd be interesting. This particular question came from a level 3 exam. And the reason why I like it, let me just get my, pen here. Okay, first thing I'm going to look at here, any of these questions, and I'll teach you how to solve a question fairly easy. I'm not really interested in most of this stuff on here. The one thing I'm going to look at is this. See this liters per minute per meter? Any question that you're going to get on the exam, they're going to say what is whatever, and they'll give you some units. See how they're like written to the side like that? So I'm going to do this. I'm going to go to the right side of your page. And trust me, this will work and you'll never think about this the same again. So you go liters over minute. And I'm doing this with my mouse, so I apologize for my penmanship, over meters. And that's going to be what your answer's in. Stack them like that, okay? And then I take the lines and I'm going to go way back here. I'm going to go way back. And I always do this because this becomes really interesting. You would agree with me that this is a volume, liters. This is a time in the middle. And this is a measure of unit for measure length, meters in this case. I'm going to look in my question here. I'm going to say, okay, I have 90. See, liters per minute. So I'm going to go 5490 liters per minute. Perfect. And then 29 meters. So I'm going to put 29 down here. If you take 5490 and divide it by 29, you should get 189.1. Simple as that. The answers is already here. The units in your question are there. And it makes it really simple to figure out where you got to put things. You know 5490 liters a minute over 29 meters will get you this answer here. So always think about it that way. Use the answer, what they're asking for, put it here. Draw those lines back and look in your question. You're given two really critical pieces of information. In this case here, our well number 7 can produce this many 5490 liters a minute per 29 meters of drawdown. So you know that at every meter of drawdown in this particular case will give me 189.31. That's how much, which is perfect. That's how many liters per minute I'm going to be able to produce per meter of drawdown. Just an easy way to think about it. Any of these questions we're going to start to throw in here is going to be as easy as this. Especially when we get into some dosing calculations, I make it very easy so you can think about it a little bit more. Okay, it's 5:02 my time, which means it's probably 9:02 your time. We're going to take a quick 5-minute break, and you can have a bathroom break or a coffee, and I will be right back.
Okay, 5-minute break, everybody. So we're gonna take a pause here. Okay, we're back.
Thank you, Ignatius. All right, welcome back here. I'll just set up the presentation again, so just bear with me for a second. All right, can everybody see that, the presentation? Give me a thumbs up if you can see that. Perfect. Great. All right, so let's talk about some of the wells. So this stuff, because I see a lot of you are on surface water, so this will be kind of a departure from what you're kind of used to. For a lot, especially here in Canada, groundwater is used. The plant that I operate here is surface water. It's about an 88 million liter a day surface water plant that I operate here. But a lot of communities use and rely on groundwater for groundwater wells, probably more so than surface water. And again, just because it's easier to treat in a lot of ways. But as we get going through the lectures over the next few weeks, we'll learn that sometimes getting some of these minerals out can prove very difficult. So we're going to talk a little bit about the well portion of groundwater here in the next little few slides here. Intakes are important, right? So if you're on surface water, you want those intakes or something that's going to protect the water coming in. And that screens out all those big parts, right? The sticks, the fish, the stuff you don't want coming into your pumps or into your water treatment facilities. Same thing with if you put a pump underground. An intake or well screen performs the same function. It allows groundwater to flow, but you don't want to have the little sand particles or stuff that's, you know, in there coming through. You can imagine if you're pumping sand through your well. The well is no different than a series of very small centrifugal pumps. And as you've got sand going through those centrifugal pumps, again, your bearings and the impellers, everything inside that pump isn't going to last a long time. So it's really important to have some sort of screening to keep the sands and stuff out. And these are your well screens. And they can be made of plastic. I don't recommend plastic because they do get brittle over time and they do break. And then hole in your screen, you get a problem and you get that sand coming through. It could be different types of steel. The problem with steel, and again, it can rust and corrode and cause issues. It can cause two issues. One issue is that it could rust and make a hole, or it could plug up, right? So it gets corrosion or crustation on it, and it actually limits the water coming through that screen. I recommend when you're dealing with anything on the water side is a stainless steel. And of course it is more expensive, but once it's in there, it usually lasts a long time. And you'll know if we do have to do any work on this well, I have to have a crane to come in to pull this well out and you can work on it. And that's very costly. So it's better to spend a little money up front to have some longevity in your well. And that is basically your intake screen. Very important job, just like an important job that we're going to see next week on the surface water side. The casing too is really important. And that is basically just the pipeline that gets driven into the ground so you can put your well in there. Typically what they do is they bring a drill in and they drill a big hole right down into the aquifer. And then they're going to drive a casing in. And this casing basically is a pretty thick pipe. And it's usually going to be a ductile iron or some sort of iron type pipe. And why? Because it takes a lot of pressure. Time breakdown. And they don't have that same strength. When you have a lot of pressure, ground pressures on plastic pipe, it could actually destroy that pipe or collapse that pipe very easy. So that usually your casing is going to be made of a metal or some sort of ductile iron, very thick, very strong. Why do we have to have that? Why can't it just be ground? Because it has to provide a seal against contamination. If we're putting a pipeline right directly to that aquifer, we do not want to have any sort of contamination. So it has to be sealed up pretty good to make sure that no rain or surface contamination ever gets in contact with the groundwater. We have to try to keep them separate. There's also something called a sanitary seal. And this is a well cap or something on top of that pipe to prevent water or animals or anything getting into that aquifer. So it's really important for, if you're going to have any sort of water well, that these things are done, that they're properly protecting that aquifer. Because if you contaminate that aquifer, what happens if there's 50 wells in that aquifer? Then you've contaminated all 50 of those wells potentially. And you don't want to do that. So it's really important to make sure you do the best job you can. Typical installation here, you can see you got a power cord coming up. Hang on, I will get my drawer guy here. So you got power cord here, and that's usually buried underground. This is your casing, the brown part, and it's ductile iron, right? It's really, really tough. And this could be 300 meters down. And this blue part here is the well cap, sanitary seal. And there's a seal under here, and it seals the top of that pipe. What I like about this well here, that it's not low, right? So if it flooded in here, there wouldn't be a problem. Water would never get into the top of this well, and you don't want that. If water gets in the top of that well, that can cause some really big issues, and that's definitely something you don't want. These are your main well components. We're also going to look at this. Now, how does water travel? And this is something that's pretty interesting. And this is called a Pitless Adapter. So what happens with a Pitless Adapter? Water's going to come up from the pump, right? This is that blue sanitary seal we saw in the last picture right here. Right, there's your electrical conduit that we saw. But water's going to come up, and it's going to leave underground through this Pitless Adapter. And basically, that is conveyance of the water out of that well. And you got to be really careful with this, because there's a rubber seal in between here. And if that gets compromised, right, making sure again that you have the right type of material, because this basically just slides in together. As the well goes in, that pitless just slides in and makes a seal. It's like a fire hydrant. It just seals together. So you got to be really careful. That's what brings the pipe, or takes the water away. And there's a large amount of contamination issues because people don't do this right, making sure that the Pitless Adapter is installed correctly. The other big one, and you see this on the test all the time, is something called grout, right? A lot of contamination happens, unfortunately, with these wells. If they put that brown pipe in, that water travels in and it goes down the sides of the pipe down into the aquifer. And to prevent that, what they do is they put this grout in, right in here. And you can see how this in the gray, they actually put, they'll use two things, concrete, or they'll use a bentonite clay. And those are the two main ones that they use to seal the sides of that pipe to prevent that water from coming down the sides of the pipe. So it's really, really important to have that grout. And that comes up as a question quite often on the test, that people put grout outside that pipe to make sure. And again, it's inserted in what they call the annular space, and that's the space there between the pipe and the ground. And it basically seals that pipe from any sort of contamination. Now, if there's runoff, right, it will come out, it will percolate through properly through the ground. It won't just short circuit through here because that grout will protect it from any sort of contamination. In Canada here, a few years ago, there was a number of wells that were in a farmer's field. And because there was fecal contamination in that field during a major rainstorm, that water got in here and it contaminated the well. What made matters worse in this case here is that that contaminated water went to the people's homes, and the disinfection portion of the treatment, so which means that the chlorine pump did not work. Chlorine was not properly added, and therefore people got sick and died because of that. And so it's very important to take this kind of stuff very seriously, because if you contaminate this well, you're not just contaminating the customer of that well, but potentially that whole aquifer. And you can see how big an aquifer can be. It could contaminate a number of different community wells and make a real mess of things. So be very aware of that. The other thing that people don't necessarily take into consideration is that sometimes when the well is done or abandoned, that they just walk away. And that's not the correct, because if you take the pump out of the well, you just got an open pipe. And some people in the past just left those pipes open, and that's open to contamination. So they have to be properly sealed up. And again, you're going to probably use this bentonite or this clay or concrete or something to seal that well from contamination to the future. So always think about that. You can't just walk away from a well. It has properly decommissioned and safely decommissioned so that there's no issues. And sometimes that's not always done. Like I'm going to harp on you guys for everything we do here. Monitoring and record keeping are key. Making sure that you're looking at all the stuff that we talked about. You monitor the drawdown, monitor how much water that well is producing. You're going to look at the motors for any sort of wear or anything different. Record keeping's key. What's changed? I'm a firm believer, no matter what treatment process we're going to be dealing with in the next few weeks, is that nothing happens just because. It happens for a reason, and it's up to you guys as operators to understand the reason why those things happen. So we're going to be looking at all these things. Record keeping is key. Why has it changed? What factors have caused this to change? It's your responsibility to observe all the trends, right? To look at what our pump is doing, our motor's doing, our conditions, the rain, the lack of rain. These are all very important factors when it comes to dealing with these pumps. You got to ensure that your pump and equipment and the maintenance of this equipment are per the manufacturer's specifications, so that you're doing the maintenance of all this. Because if you're not, you can be putting yourself and your community at risk. I got a question here. Have you ever had one of your wells getting contaminated? It's very, not personally, but if a well gets contaminated, because think about some of these really slow moving big aquifers. It sometimes could take 100 years to get that water to the well, so contamination won't show up right away. It's better to make sure that your well's not ever getting contaminated. If a well is contaminated, sometimes it's no good anymore, and you'll have to drill that well or look for another water source. And again, that's very costly and very hard to do. Sometimes on smaller contaminations, stuff could be flushed out, or you know, depending on how widespread that contamination was, you can disinfect that area and pump a lot to try to bring more fresher, non-contaminated water in, but it's a very, very difficult task. So good question. Very important to make sure you don't get it contaminated in the first place. Here's some stuff that you're going to be looking at, and all these items here could potentially be issues for your pump. You can have physical wear, right? And we talk about sand pumping. We don't want to pump sand because pumps don't like that. Biological fouling, and what happens here is iron bacteria forms, and that orange paste. It's very awful, and it's really hard to get rid of. And sometimes you have to do something called shocking the well, which is adding disinfectant, usually in the form of chlorine, to a well, to the bottom, to dissipate the iron bacteria. It could be plugged. It could be plugged by, you get some clays in here, or something happens below. The metal of the screen can get plugged because of incrustation. Keep in mind, there's a lot of minerals in groundwater, and it could easily adhere to the screen and cause hardness, scaling, and it plugs these wells up. You can overpump. And we talked about overpumping. Think about it's like that straw. If you're sucking too hard on that straw, the straw collapses and causes issues. Clogged or collapsed screen, and that causes that. So there's a number of issues here, and it's you guys as operators should be aware of different issues. Let's switch gears. Picture right there is actually, this is where I live right here. So this is the lake where I get my water from. This is, you can see, again, I have a lot of mountains and whatnot. I don't always have snow here, but this is a nice summer's day in this particular photo, but gives you an idea of the amount of water I have available for me. I take water from both this lake here, which is Lake Okanagan, and I also get it from a creek as well. So I have two sources of water. Again, most of this comes from snow melt from those mountains you see in the background. It gets, you know, it's a moderately hard water. It's not super soft, it's not super hard. So when we talk about surface water, it's rainwater, it's snow melt, it's some runoff. It hasn't been in the ground at all, or very, very short period of time. So it's open to the atmosphere. And again, these are the creeks, ponds, canals, wetlands, whatever it is. If you can see it, it's surface water. There's your four big ones, right? Lakes and reservoirs sometimes are the same. Reservoirs are usually man-made, or their water has a dam, or it's impounded some way. Rivers, streaks, creeks, and streams. A lake is any inland body. And again, usually a lake is fed from both groundwater sources. And where I use the word reservoir, it's a natural or artificial pond, right? It's usually sometimes where we store water just before we treat it. Usually the best definition is that it's controlled or regulated, some sort of inlet. It's usually termed reservoir. Stream, again, streams and rivers are moving bodies of water. It's moving versus a lake, which it's not necessarily moving. A river is just a bigger version of a stream. The thing about surface water is we use it for recreation, industry, transport, agriculture. Again, we use it for human consumption. Lots of activity. And this word here, watershed, becomes really important because it's the bigger challenge now. It's not just where we take the water from. It's, again, looking at the bigger picture. Where does this water come from? How do we keep it safe? How do we keep it safe from us humans and the effect of pollutions from whether that's industry or agriculture or whatever it's going to be? We have to look at all this stuff, right? Surface water replenishes the oceans, and we need that continuous supply of fresh water. We need that. It keeps the oceans alive. We need that natural level of saline, and it moves in this cycle. It's really, really important. This always shows up on the test, a watershed. And again, it's the drainage area of land that directs all that rain towards a certain point. So typically, you know, your lake, your stream, your river is going to be fed by something, whether that's rainwater, snowmelt, or whatever it's going to be. It consists of all these lakes, rivers, streams, reservoirs, wetlands, and all this stuff, all interconnected. And this is a watershed. Here's a typical watershed here, and this is really interesting to see because for us here, and you saw my mountains, snowpack is huge for me because what happens over the summer months that the rain and snow melts all that, and so we have a steady supply of water going down this basic stream into a river. Now you're going to see some lakes sometimes, and they could be because of rain or snow or groundwater, you know. But typically, for us anyway here, it's all coming from some sort of snowmelt or precipitation. All that precipitation through all that land, which is called the watershed, and it's going to flow to a certain point. This is the point here. All that water from all this, whether it's precipitation, all these little creeks and streams and lakes all end up here. And typically we might have a water treatment plant anywhere in here, but anything that happens in this area in your watershed will affect your water. And it's really important to understand what that is, whether that's industry or any sources of contamination should be really clear, right? So it's important to see what are things in here that could actually do damage to us. There are some problems here. Let's talk about some major ones, especially in surface water. Algae is a big one. Algae is always a big, and again, what happens when water gets contaminated or has lots of nutrients in it, plants will grow. And that could come from fertilizers or anything that got washed into the water or into the watershed. And algae does a couple of things. The pH increases and dissolved oxygen increases. Filter clogs. It creates some really nasty odors for algae. But the biggest problem with algae is that, and you guys need to be aware of, is that if I have lots of plant life or algae in your water, during the day, right, the pH increases a bit. So the pH is pretty good, right? And it creates oxygen. any plant, right? It takes on CO2 and it gives off oxygen, and it's fantastic. You put some oxygen into the water, the pH goes up. But at night, the pH decreases. It makes the water acid. It takes oxygen out of the water. It makes CO2. And CO2 is an acid. And how you can remember that is think about a cola or something like that, okay? And cola is basically a very acidic drink. And what is it about cola that makes it acid? It is the carbonation, the CO2. Because really, Coca-Cola or any of the Coke products like that are going to be syrup, sugar, in water. That's all it is. And it's not acid at all. But if I add CO2 to it, which is that carbonation, if you bubble CO2 in it, it turns into an acid. Think about water. Water, if you drink, is not acidy at all. It's pretty neutral. But if I bubble CO2 into it, make it sparkly water or carbonate, it actually is acidic. So the same thing happens here. At night, the pH decreases because the plant life, and algae in this case, creates CO2. So what happens, I see a lot of this, that at night in little bodies of water that have a lot of plant life or algae, that it creates this acid environment at night. Fish die, and the fish wash up on the shore, and the next morning people see this and they go, uh-oh, what happened here? Something's wrong. Then they go and do a test of the water and the water's fine. Because during the day, plant life does the opposite. It puts oxygen into the water, brings the pH back up, everything's okay. It's at night, it can cause some really big problems. So always remember that pH will change for plant life. During the day, everything's okay. At night, it's not okay at all. It produces CO2 and bubbles that into the water, causes it to be very acidic, kills fish, makes a mess. Some things to think about too is that any sort of algae or organics, and we're going to learn about this next week, is that it makes some pretty awful odors, right? That's your grassy, fishy odor. And that's a big complaint that a lot of customers have, right? My water smells like fish or grassy, yuck. And that's usually because there's some plant life in it. And when you mix that with chlorine, the smell sometimes gets worse. There's a threshold odor number, and that's how they measure smell. That smell and taste is measured in something called a threshold odor number, or a TON. There's some different nutrients that are out there, and these are the nutrients here that we don't want. What happens with these nutrients is that this promotes the plant life or promotes the algae growth in your lake or your water source. And the more algae in or plant life in your stream, the more potential that you can have for problems. And we talked about the problems of making that water really acidy. Not a good thing at all. Also, too, some of the things you got to think about if you start getting a lake that has very little oxygen because it's all being used up by the plants, is that it can actually start reducing sulfates and creating those gases like it does in groundwater, that H2S gas, that rotten egg smell. And that's just a good indicator that you have too much organics or too many issues in your lake. It's becoming dead. It doesn't have enough oxygen to support life anymore, and it becomes a dead lake. It's a problem. It can actually start reducing iron and manganese, so you start seeing this come out of water, and that's not what you want to see. It could be really bad here. Organics are another bad thing, and we talked a little bit about organics when we talked about disinfection. And again, what we don't want are these THMs, or trihalomethane precursors, and anything color and organics put in a disinfection, and we learned about that last week. And so when we have these organics in that water, they basically, when we add the disinfection, trihalomethanes and haloacetic acid are our two disinfection byproducts. And that's the problem. Get more of these in there. Organics we don't want, but they're in there, and we have to realize that they are, and we have to look at ways to remove long before we do disinfection. We'll talk a little bit about thermal stratification. Now, this might not be necessarily an issue with some of the larger lakes, but definitely it is with some of our smaller lakes, it happens. So in shallow reservoir or lakes, summer water temperatures and oxygen will change. And that depends on wind or temperatures. As surface temperatures rise, a relation in bottom waters, the layers within the lake will change. We'll look at this here. You can see here that there's three main layers. And the upper layer here, we'll call it the is it's going to be up. The second one, we also call that thermocline. That upper end is usually warm. The currents are warm. It usually it's subjected to the sun, and it's nice and warm. Keep in mind, warmer temperatures have less oxygen. As we get to the middle there, the yellow layer, we can call that the thermocline. Any point past that into that blue, it gets really cold. It could be up to 4 degrees at the bottom of that. 30 degrees at the top. So that's a problem. So what happens now is that as, say that the blue layer is 4 degrees and it's really, really cold outside, and all of a sudden that red layer starts to get 3, 4 degrees, what happens is a turnover happens so that the water at the bottom flips over to the top. And they call that turnover. We see it here all the time when we have big temperature swings. That all that stuff at the bottom, which hasn't have a lot of oxygen, it hasn't seen a lot of light. It's got a lot of plant life and a lot of stuff, like rotten over time. It actually gets stuck to the top, and and that warmer stuff will start to flip to the bottom. And unfortunately, what you see here is that this is where you can get taste and odor issues, because when you have reduction of oxygen at the bottom, when we saw that over here, it could reduce bacterias and make that H2S gas and have iron and manganese that comes out of solution. You can have all these nasty things in this turnover. And that's what it is. It's all these layers start to mix. If they stay apart like this, we're doing okay. But as temperature changes, that's a problem. Wind too, right? So if you get a cold wind and this all of a sudden starts to cool off, these layers can start to mix up a little bit. Probably not so common for super deep sources, but for here, if your draw off is in the blue part, that's where your intake water treatment plant, all of a sudden if this starts to mix, your water quality is going to change very quickly, and it might not be a good thing. So you always need to be aware that if your air temperature is going to be changing, potentially your water quality is going to change even though your water comes from a deep. And that's called turnover. And this whole thing is called thermal stratification. Reservoir management is also fairly important too. So picture here, I like this. This is really a good way to do business, because what you see here is there's no trees or bushes or anything that is in this reservoir. You get this nice rock bit here, and it protects everything, right, from plant. Anytime you have plant life in your reservoir, that there's potential for organics, right? Think of the tea in the leaves and stuff, and gets into some trouble there. Any sort of discharge like wastewater or fertilizers or any of these things we talked about earlier can contaminate your reservoir. So making sure that anything in here. Now, if you have a lot of fertilizer or any of these organics, or I guess would be a better term is nutrients, that could cause plant life to grow. And we talk about what happens when we have plant life. It becomes a problem. One of the things when we go back to DO and algae, what's a way to get rid of algae? And one of the biggest ways is to use a product called bluestone or copper sulfate. Now, I thought I had it in here, but I guess I don't. Here it is right here. Copper sulfate is used to get rid of these algae. Okay, so if you have an algae problem, you'll use copper sulfate. So you got to be a little bit careful though, because the copper is a MAC. And so what happens is that you can overdose copper into your source water, but copper sulfate or bluestone is used to deactivate or remove a little bit of those algae so it doesn't clog your filters. Another thing a little bit about algae is that when combined with chlorine, it produces a really awful smell. It smells like a medicine-y type smell, and it's actually quite awful. It will also any sort of your screens or any of your intakes and stuff. So it can get pretty awful very, very quickly. Here we go here. And you can see here's some algae. This is pretty awful looking. Copper sulfate pentahydrate, also called bluestone. So this is a good example of an algae bloom. And you can see this green awfulness here. This is something definitely you don't want to see in your water source. You add this you know, it will clog up your filter very quickly. And again, if you add chlorine to this water, it's going to make a very, very awful smell. And that's something that you definitely don't want in your system. Let's talk a little bit about waterborne diseases that are out there, right? And we're going to use those word pathogens again. And we know pathogen are the disease causing, and they can be bacteria or cysts or viruses. We know there's a lot of bacteria sitting around in here too. And again, but you know, there's good bacteria in yogurt and stuff. There's you know, bacteria is not all bad, but there is some bad ones that we need to deal with here. One of the ones that we're going to go over again and again, this is our first brush, and these guys are coliforms, and that's a group of bacteria. Coliforms are found in soil, in the air, and in some water, and they're actually inside us, right? All warm-blooded animals have coliforms inside us. There's two types, right? There's a total coliform and fecal coliform. Now, total coliforms are just saying, hey, there's contamination here. Whereas the fecal coliforms, they are usually associated with sewage, or that's a really bad thing. The absence of fecal coliform does not necessarily indicate that other types of bacteria are not present. This is just an indicator. Think of it as guilty by association. If coliforms are in there, chances are there's some other really nice in there. So keep that in mind. It's guilt by association. We call these things indicator organisms because there's so many bacteria in the water. you can't test each one of them. So we have to pick one that's representative. And if it's there, chances are other things are there too. So we use these guys, total coliforms. And again, they're resistant to chlorination. They are a good indicator of how well your treatment is. It's definitely, I can see total coliforms from wood products or soils. So it doesn't always mean that there's contamination from humans. It could mean other sources as well. Still, you do not want any total coliforms in your water. Fecal coliforms or E. coli, that's the nasty one. That's the ones that's found in the feces. And basically, it's associated with contamination. And again, the E. coli is the most specific indicator of fecal pollution. And again, if it's in your water, it's a real problem. E. coli can make you very, very sick. There's also something called heterotrophic bacteria. I actually measure these as well. So when I go out into my system, I actually test for heterotrophic bacteria or heterotrophic plate count. And it's an indication of the general bacterial population. I actually use PC in my system to dictate where I have to flush my system. For those of you who also run distribution networks, I find this really helpful for me. It tells me, it doesn't mean that there's a public health risk, but the bacteria count in a water system allows you to tell me where my water might be going stagnant. It's a really good way to figure out where I need to flush or where I need to let some water go in order to keep my system fresh. You're also going to look at pH and temperature, color, turbidity, taste, and odor. And again, your customers are going to judge your water. That's what happens, right? They're going to say, oh, this smells or looks horrible. But all these things we talked about, pH, temperature, color, turbidity, taste, and odor, are all very aesthetic. None of these things are going to cause health problems. Again, they're physical. They cause issues. Again, they might affect different treatment processes to get rid of everything, but these are to make your customers happy. Again, there's organic and inorganic compounds, and they could be introduced through processes, in the industry, or it could be in there or naturally occurring. Some are toxic, which are not very good. And again, some compounds can affect health, are regulated by your particular water purveyor. Some new stuff too, and it's not widely, but there is radiological characteristics too. There's 200 radionuclides. Again, also potentially, if you're in a zone where there's lots of volcanoes, there is some definitely radionuclides around there. And again, always be aware that this exists. One of the big things too is source water protection. Again, this is part of the multi-barrier approach, right? It's not just the barriers that we talk about with water treatment, but also the barriers of making sure we're protecting that whole watershed that we talked about, making sure that there's no industry or anything that happens. We have a lot of stuff here because we have mining and we have lumber and pulp and paper, right? They cut the trees down. We have definitely forest fires here, lots of fires. And now all this in our watershed will affect our quality of our water. We use a, and again, this is to prevent or reduce contamination. It protects from source to the tap. Everything is in, it's not just the treatment in between, but also looking at the source, all the way from when it leaves our treatment plant to our customer's tap. Part of this is source water protection, making sure that it's protected and that there's no ill effects from any sort of industry. There's a bunch of contamination that can happen: discharges, spills, runoff, infiltration, all this stuff, right? There's point source pollution. So there's widespread pollution or pollution from a single event or an industry. It's up to us to protect our whole watershed and control who uses our watershed, whether that's human or companies or industry. It's very important to making sure that there's controls in place to protect everything as a whole. We talked about maintenance, right? Making sure that we're abandoning those wells properly and that there's protection for our wells. They're in the higher spot. Maybe there's a building built over them, just protecting them from contamination. So that's it for today, everybody. So I hope you learned a little bit for us for chapter 4 or week 4. We won't do too much from the standpoint of quizzes. We will do a few more quizzes on our next set. What we're going to do, if you want to read ahead and look at some of your support documentation, is we're going to do intakes, coagulation, flocculation, and sedimentation process of water treatment next week. It's a pretty important chapter. Now that you understand groundwater and surface water, we're going to a little bit more of the treatment processes. Now that we got water, we know where it comes from, we're going to get it to our plant now. And now let's start treating it and learning about how we treat this water. So we're going to get into the more of the meat and potatoes part of our treatment in the next few. So we'll be doing the treatment of coagulation, flocculation, and sedimentation next, then into filtration, and then into some other water treatment stuff like removal of metals and removal of hardness. And that's going to happen in the next 3 weeks here. So I thank you for joining me today for my lecture. And I hope you guys have a great day today. Thank you very much.